There are two ways an infrared spectrum can be plotted. One is using absorption and the other one using transmittance. The one in this slide is an example of an absorption spectrum. On the x-axis, you have something called wave numbers. And wave numbers, inverse centimeters, is the inverse of the wavelength. And the reason why is the x-axis is giving wave numbers is because it makes the units nicer to work with. You will see that we are working with units that range between 4,000 and 400, give or take, inverse centimeters. In the y-axis here, we are representing absorption. And as you see, the example of this particular band that appears here, the band rises upward because it represents the amount of infrared radiation that has been absorbed by that particular bond. Most infrared spectra will be given in transmission mode. So again, the x-axis is wave numbers in inverse centimeters, and what it's shown in the y-axis is the transmission, the amount of radiation transmitted. And that means that the spectra, the infrared spectra, are the bands appear pointing downwards. And that is the most common way of giving infrared spectra in chemistry. The absorption mode tends to sometimes be common in forensics, but in a typical chemistry journal, in a typical chemistry book, you will see all the spectra with the bands pointing downwards. Because it's a transmission, the spectrometer has been run in transmission mode. When you're describing an infrared spectrum, you typically describe bands as weak, medium, or strong. A strong band will be one that covers most of the y-axis, and that can be typical, for example, of the carbonyl group. The carbon double bond oxygen group tends to give these very strong bands. Then you have medium bands, and you tend to describe bands as medium when they cover roughly half of the y-axis. And finally, you have weak bands, and those tend to be the ones that are small, a third or even less of the y-axis. What will determine if a particular bond, a particular set of atoms will give a strong, a medium, or a weak band? Well, it depends on the magnitude of the dipole moment for that particular bond. So, for example, when you have a bond that produces a strong, when you have a strongly polar bond, for example, a carbonyl group, the carbon double bond oxygen group, you tend to have a strong band. When you have a bond that is medium polarity or an asymmetric bond, so they tend to give a medium band. And when you have a very weak polar bond or a symmetric bond, for example, here, this molecule is very symmetric. Then you tend to observe very small bands, very weak bands, or is sometimes even not observable. And I have an example later on how much difference can it make. For example, in this case, for an alkane, a triple bond, how much difference in the intensity of the band it makes if the triple bond is in the middle of the molecule, or if there is a certain amount of polarity in the molecule and the triple bond is in one side. This is an example of how the change in the dipole moment of the molecule influences the strength of the infrared band, or if the infrared band will appear at all in the spectrum. So here's the molecule of CO2, and here is the example of the symmetric stretching vibration of CO2. And this means a non-polar molecule. There's no change in the dipole moment. So this band is inactive in the infrared spectrum. It does not show. This one, however, although the molecule is still symmetric, the antisymmetric stretching vibration does produce a change on the dipole moment, and then that's what it reflects as a band in the infrared spectrum. And then finally, there's another band associated with carbon dioxide, and it's the bending mode. And as you can see, the band is much weaker. Bending modes typically originate weaker bands than stretching modes. In the case of the molecule of water, the two stretching modes, the symmetric and asymmetric ones, are both active in the infrared. They all have associated a dipole change, and they all appear in the infrared spectrum. And interestingly, in the case of water, as exception, the bending mode is stronger and reflects in a larger band in the infrared spectrum. The strength of the bond will affect the wave number, where in the infrared spectrum the bond is going to appear. If you think of a bond as a spring, and if you think of a strong bond as a stiff spring, difficult to stretch, then you're going to need more energy to make that spring vibrate. So that is why stronger bonds need more energy to vibrate. They will absorb at higher wave numbers. So if you can see here, for example, example of carbon-carbon bonds, or carbon-oxygen bonds, or carbon-nitrogen bonds, when you move to single, double to triple bonds, when you increase the bond order, the frequency, the wave number to which those bonds absorb increase. The influence of the strength of the bond can also be observed when we look at carbon-hydrogen bonds. And the strength of the bond is different when the carbon making that bond is an sp3 carbon involved only in carbon-carbon single bonds, an sp2 involving carbon-carbon double bonds, or an sp, a carbon involved in a triple bond. And as you can see, the bond strength increases when you move from an sp carbon to an sp2 carbon to an sp3 carbon, and the frequency, the wave numbers to which the carbon-hydrogen bond absorbs also increases slightly when you move from a single to a double to a triple bond, from an sp to an sp2 to an sp3 carbon. Mass also has an effect in how the molecules vibrate. So it also reflects in a different position of the bands in an infrared spectrum. Heavy masses on a spring will vibrate more slowly than lighter masses. So heavier atoms will vibrate at lower frequencies than if they are lighter. So for example, if you compare the vibration, the infrared spectrum of deuterated water compared with normal water, you will see that the band that corresponds to the oxygen-hydrogen bond, or the oxygen-deuterium bond, in the case of the deuterium, with a heavier mass of deuterium, that band appears at considerably a lower frequency. As I mentioned before, in general, bending modes, bending vibrations are of lower energy than stretching vibrations, and the bands tend to be weaker. Not always, but they tend to be weaker. Generally, it's easier to bend than stretch, so you need less energy for that. So the bands the bending vibrations have a lower energy, and they appear at lower wave numbers. So we've got, for example, here the infrared spectrum of hexane in transmission mode, and you can see that the carbon-hydrogen bending mode appears, the bands are smaller and at lower wave numbers than the bands corresponding to the carbon-hydrogen stretching modes.